Hello everyone, welcome back to this channel. Now someone has requested me to explain the exercise from the Kaggle. Here you can see different types of courses they have provided. From the learn section you can find them, and here you can select any courses. So I have selected this intro to deep learning because someone has requested me to do the exercise. So I will create a playlist where our main focus will be doing these exercises. Okay. So I assume that you have an idea about deep learning. Now you want to practice, you want to see the real implementation, then this playlist will be very helpful for you. First, we will start with these lessons. We will revise the tutorial and then we will do the exercise. This is our main emphasis for this playlist. Okay. So if you have an overall idea about deep learning, this will be very good for you. Okay. Now let's start it. First, I will click on the tutorial. You can just go to this website, click on the learn, and then you can visit this. Okay, simple. Now see, I hope you know all these things. So our main objective is to revise the things. Now my question is, what is deep learning? It may be your interview question. And what is the difference between machine learning and deep learning? So you can say that deep learning is just a part of machine learning, a subset of machine learning. And to be more appropriate, it is an approach to machine learning where we use neural networks. Right? Okay. So in traditional machine learning algorithms, we didn't use neural networks, but here we have used neural networks and we are trying to predict the values of weights and biases. Okay. Now first, what is this? This is a neuron, one input neuron. X is the input, W weight, B means bias. Why bias? Can you tell me why bias are included? Because you can think that anywhere you cannot get any direct relationship. There are some other things which always impact, right? So that's why we include the bias. Y is the output. So output equals to W into X plus B. Okay. So now our job is to find the W so that whenever we get any input later on, we can simply apply the weights on the input and we can predict the output. Right. So you have data sets. Now you train the data sets. You try to find the W so that later on the input we can apply the W and we can find the output. Simple. This is the basic concept. Right. Now how it is done? Can you tell me? This is done by calculating the loss function. What is the loss function? Loss function means suppose in your data set you already have the output. Those are previous data, historical data. So you have the output in case of supervised learning. Now your job is to find what is the predicted output and what is the real output. So you calculate the difference, that is the loss. That means you are not predicting correctly. You are making some mistakes. Okay, there are some amount of loss. For calculating loss, there are many loss functions. You can use any loss function depending on your requirement. Now on that loss function, you calculate what is the loss and then you try to minimize the loss. Minimize the loss. How to minimize the loss? By changing the weights. So you have to calculate for which weights and for which bias the output, the loss is the minimum. Right? If you find that W and find that B, then you can use those W and B to predict any future output. This is the simple logic. Okay, now see here, they have given a good example. They have provided sugar as input and calories as output. Okay, so you have data set where they have sugars as input and calories. Okay, so from that, from in that data set, you train your model and you find that this is the value of W. So that later on, whenever you get some sugars, you apply that W and you calculate the calories. Right? Okay, now see here, this is for multiple inputs. Okay, so not only sugars, you may have some other inputs also. So for that, every input you have a weight W0, W1, W2, and there is a bias. Now you are predicting the output Y. Okay, so your job is to find for which weights and biases the loss is the minimum. Then you get your weights and biases, you can use them on your inputs and you can predict the output. Simple. Okay, now let's create our first neural net. Here you can see from TensorFlow import keras. So from TensorFlow library you have to import keras and you have to import layers. These are required for creating the linear unit. Okay. Now first create a network with one linear unit. So module equal to keras dot sequential layers dot dense units 1 input step 3. Here units equal to 1 means the output will be 1, input step equal to 3 means in the input you have 3 parameters, maybe sugar, added sugar, cholesterol. Okay, so it will look like this. So you have one output and three inputs. Okay. Maybe this one is sugar, maybe this one is added sugar, maybe this one is cholesterol. Okay. So they are taking three inputs and one output, single neuron. Okay. See here they have explained. We defined how many outputs we want. Output units equal to 1. So we want one output. We want to know what is the calorie value, right? So we are just predicting the calories. So units equal to 1. And the second argument, this is the second argument, input step. So we tell Keras the dimension of the inputs. Setting input step equal to 3 means that it will take 3 features. Sugar, fiber, protein. Okay. Now they have given a your turn. That is our main focus. Now let's do this. Find a linear model for the red wine quality data. So if you click here, you will come into this exercise page, and here only you can run the cells. See, they have told that we have learned the building blocks, and now if you run this, just ignore the warnings. This is for plotting, like white grid means grid plot. Okay, and these are used to import the data set. Anyway, from here our job starts. So just click here, then it will execute. Okay, so you can see the data set. And you know that to download dataset, you have to use import pandas as PD. Now pd.read CSV function, and this is the link of the dataset. Okay. Wait for watching the first 5 rows. You can see this is fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, alcohol quality. These things are given in red wine dataset. Okay. Now they have provided some exercise. So we will solve this. You can get the number of rows and columns of a data frame with the shape attribute. You can tell that because we have already studied that. If you use dot shape, then they provide you rows and columns. Now let me run this one. Just see, sorry. Then I think import pandas. And now if you just see 1599 rows and columns means 12. Fine. You can see 12 columns. Okay. Now, how can we predict a wine's perceived quality from the physiochemical measurements? The target is the quality. Here, see, some have good quality, some have bad qualities, depending on the ingredients. Now, what is the question here? The target is the quality, and the remaining columns are the features. Fine. How do you set the input shape parameter for a Keras model for this task? Now, let's do the exercise. First, you have to write the code here. They have given you the question. You have to guess the answer. Then you can check also. Fine. If you run this, then it will show you whether your answer is correct or not. So, suppose if I randomly write something like 13, then the input, first of all, it will be in third bracket, and then it will show that it will be incorrect. Okay. Anyway, so we have to find what is the input set. How can we tell that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have also got it from here that it has 12. Now, what is the output? Output is the quality. So, you have to remove the quality. Then, the remaining are the features. So, input step is 11. That means we have to give 11 features as input. Clear? 11 features as input, quality as output. Okay. So, here the right answer will be 11. Now, if I run it, correct. Okay, so this way you can solve this. Now here they have also provided hint and solution. If you can't find the answer, then you can just click here. Then it will give you the hint and it will give you the solution also. Fine. Okay, now next do the next one. Define a linear model. Here you have to just define the model. What will be the input and what will be the output. So you just have to write keras dot sequential, and inside that layers dot dense output units equals to one output, comma, input shape. Input shape means how many input features you want to give, that is 11. Right? Now if I run it, sorry, you have to give in the array. Let's see. Okay. Here also you can just check the solution. You have to just click here. You can see the hint or you can see the solution. Okay. Fine. We have just created a dense layer. Okay. So we have 11 input features and one output. Fine. Okay, now next look at the weights. So you just want to know what are the weights and biases for this. So you have to write model dot weights. Then you can see the weights and biases. See here. Do you see how there's one weight for each input? And notice that there does not seem to be any pattern to the values. Before the model is trained, the weights are set to random numbers. Right? Here also you can check the solution. Model dot weights. Okay. Let's print this because we want to say the weights. Just run it. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 weights for 11 features. Clear? Now let's see the output plot. Here imported TensorFlow, matplotlib for plotting, and C1 also can be used for plotting. Here they have created the model, input step 1, and this is the linearly spaced some values, minus 1, 1, 1.0, minus 1, 0, 1.0, okay, and 100 is a linearly spaced values. Y equal to model dot predict, and then they have plotted the figure. So you can see that weight and bias. Okay, so you can plot this. Now in our next lesson, we will study make your models deep. So today, summarize the things we have learned. We have learned how to take any data set. We know these things already. And then we have created a model and we have seen their weights and biases. If you want, you can plot the weights and biases. Okay. So I hope you have enjoyed doing this exercise. And if you want any other improvement, if you want me to explain anything else, please let me know in the comment section. Because my wish is to make your learnings very easy, smooth, and enjoyable. Okay. So bye. Happy learning. Hello everyone. Welcome back to this channel. Sorry for uploading video late as I was busy with some works. Anyway, let me tell you the whole setup. Okay. First, we started this course, Intro to Deep Learning. This is in Kaggle Learn. You can click on Learn, then you will be able to get many courses. From there, we selected this one, Intro to Deep Learning. Okay. In our last class, we studied about this one, a single neuron. First, we understood the tutorial and then we did the exercise. Okay. So today we are going to do the deep neural network. First, I will tell you the concept, whatever it's written here, then we will do the exercise. Okay. In our last class, we studied about a single neuron, and now you will understand how to create a deep neural network. Okay. So we are going to see how we can build neural networks capable of learning the complex kind of relationships deep neural nets are famous for. Why deep neural networks are famous? Because they can learn the complex relationships. Okay. For that, we can use different layers. In our last class, we studied how to create a single layer neuron. But now we can create different layers of neuron. Okay. The key idea here is modularity, building up a complex network from simpler functional unit. Every unit is simple, but combining them will create a complex network, which will capture the complex relationships from the data. Simple thing. Okay. Now we will see how to combine and modify these single units. Layers. You know what is layers? Layers means, say here, this is the layer. This is a layer. This is a layer. Input layer, dense layer, output layers. Okay. So typically organize their neurons into layers. When we collect together linear units having a common set of inputs, we get a dense layer. This one is a dense layer because here we are getting common set of inputs. See, this one, this single neuron is getting from x0, x1, 1. These are inputs. Same, this layer also, sorry, this neuron also getting all these inputs x0, x1, 1. So combining all these layers we can call dense layer. It is also getting same inputs, it is also getting same inputs. So collecting together all the linear units having common set of inputs creates a dense layer. Clear? So here this is the input layer, this is a dense layer and this is an output layer. Your outputs sometimes may be one output or sometimes it may be more than output depending on which kind of prediction you are doing. If you are doing classification, like you want to know whether the picture is of a dog or a cat. So that may be two types of outputs. It may be dog, it may be cat, right? It may be 0, it may be 1. Okay. Or suppose if you want a single number, like the price of a flat. So there you will get a single value. There you will have one output. So depending on the types of prediction, the output layer may have single output or it may have multiple output. Okay. Now see, you could think of each layer in a neural network as performing some kind of relatively simple transformation. Through a deep stack of layers, a neural network can transform its input in more and more complex way. In a well-trained neural network, each layer is a transformation, getting us a little bit closer to a solution. This simply means that when we create different layers, each layer is capturing a bit from the input. The next layer is capturing some more features. The next layer is capturing some more hidden insights. Okay, so each layer is giving some more information which is bringing us to the solution. Okay, now let's read the activation function. Activation function simply means that it can capture the non-linearity from the dataset. Two dense layers with nothing in between are no better than a single layer by itself. Dense layers by themselves can never move us out of the world of lines and planes. It simply means that if you create only dense layer, then it will always capture the linearity in the relationship. But what if the dataset has some non-linearity? For that, we need activation functions. This is an important interview question. They may ask you that why do we need the activation function? Then you have to say if your dataset has some non-linearity, then you have to use the activation function. Otherwise, the non-linearity from the dataset cannot be captured from the dense layer. Clear? So you can say that without activation function, neural networks can only learn linear relations. Okay, if you don't know about activation function, then you can read this blog. It's written by me. Here I have explained what is sigmoid, what is tanh, what is ReLU, and what is softmax. This will give you basic idea about what types of activation functions we can use. Okay, this is very important for your interview part. Anyway, let's come back to our main focus. Okay, now see, an activation function is simply some function which apply for each of the layers output. The most common is rectifier function. What happens, whatever your output is from the dense layer, whatever it has captured, after that we apply an equation on that output, right? Like it may be ReLU, it may be sigmoid, it may be tanh. All these are activation functions. Even in ReLU also there are different types of activation functions like leaky ReLU, parametric ReLU, LU. Okay, so these are nothing but some equations. Why these equations are applied? Because sometimes your output may be huge, maybe big, or maybe very small. So what you have to do, you have to just apply the equation, that means the activation function, and bring the output into a range. Then your non-linearity will be captured easily. Simple. Anyway, the rectifier function has a graph that's the line with the negative part rectified to 0. Applying the function to the outputs of a neuron will put a blend in the data, moving us away from simple lines. Okay. So when we attach the rectifier to a linear unit, we get a ReLU function. For the reason it's common to call the ReLU function. Applying a ReLU activation to a linear means output becomes, this is the equation, max of 0 comma wx plus b. You simply can say that whatever is the negative part will become 0, because you have to take the maximum of either 0 or the value. If the value is negative, then you are simply ignoring, you are taking the max value, which is the max value, that is 0. That means the negative part will become 0. Okay, so the diagram is like this. This is the graph of ReLU. This is how it works. So whatever your output is, if there is anything negative, if the output is in a big range, then the negative part will be 0 and the positive part will be captured. So it will just give you a bend in the data. Okay, this is W. W is, what is W? W is the weight. X is the input. B is the bias. So output will be Wx plus B. If it is negative, then you will take 0, because maximum value is 0 here among the 0 and the negative one. Okay, so you are simply ignoring the negatives. I think you have to study activation functions in details if you don't know. Okay, we are just revising the things here. Okay, now the next is stacking dense layer. You understand what is nonlinearity? Now what happens? You are taking many neurons. So here also you are taking dense layer, you are putting activation functions. Again you are sending it to next layer. You are putting some dense layer, you are putting some activation functions, and combining all of these, you are getting the output. So this neuron is capturing some data, some value. This neuron is capturing some value from the data set. This one is capturing some value on the data set. By putting activation functions, you are bringing them into a range. Again, you are applying dense layer. Again, it is capturing some value, some formats. And again, you are putting some activation functions. And finally, you are getting the output. So this is stacked dense layer, making a fully connected network. Fine. The layers before the output layers are sometimes called the hidden layers, because this one you can see, but you cannot see what is happening here. I hope you know that if interviewer asks you a question that what is the main problem with deep learning, then you can say that we don't know what is happening inside. Sometimes the output may be odd or may give something which is not so usual. So if your the client questions that why the output is like that, then you will not be able to answer why your model is behaving like that. You don't know what is happening inside. In machine learning, you know what is happening. That is transparent. You can see that why your model is behaving like that. You can explain. Okay, but in deep learning, these layers are not explainable. You cannot explain what is happening inside. So that's a kind of problem with deep learning. Anyway, that's not our topic. We will only know that why these are called hidden layers, because you cannot see them. You can see the output only. Okay. Now notice that the final layer is a linear unit. That means no activation function. Here they have not applied any activation function. You can, but here they have not applied. That means the network is appropriate for a regression task where we are trying to predict some arbitrary number value. For classification, classification means you have to give a boundary. You have to say either it is 0 or it is a 1. So there always you will need an activation function. But if you are working with regression, means it will give you a value only. As I said, it will give you the price of a flat. It's generating a number, a numerical value. Then you may avoid activation function. So it depends like on which you are working. Okay. And even which activation function is better, whether ReLU, whether TANH, whether sigmoid, you can experiment with all these things while you will doing these things. You are creating the layers. You can use different kind of activation functions to check which one is giving you the best output. Okay. Let's do this one. So this is a package where we have to import the keras, we have to import layers. Okay, this will help us to create the dense layer. So we are just creating the model. We are just creating this layer. So we will tell how many layers will be, sorry, how many layers will be there. One, two, here like two layers. So you may have three layers, four layers. How many units will be in the layers? So all these things are created here. So first we are creating, these are the hidden ReLU layers. Layers.dense units equal to 4 activation ReLU input step 2. Input step, you know, input step is simple. That means your data set has two inputs, one output. So that's why input step is 2. Okay. Activation function, they have used ReLU. ReLU actually performs better in most of the cases. That's why it's so famous. Okay. And now the number of units. In the first layer, you are giving 4 units. Like see here, it is given 5, but if you want, you just create 4 units. Okay. In the second layer, you give 3 units. Means in this layer, uh, sorry, here also it is 4 units only. One is the bias. Okay. So here it is 4 unit and here it is 3 unit. So units 4, activation ReLU, input step is 2. Second layer, unit 3, activation ReLU. Okay, so you have created two hidden layers. Now you have to create the output. Okay, so the output is unit equal to 1 because you want only one output. Fine, and you have not used any activation function. If you have used, then you have to write comma activation equal to ReLU. Clear? Now, be sure to pass all the layers in a list. All the layers must be in a list. See here, the list has been started from here. Okay, and inside you can create more layers. If you want, you can create some other layers with different kind of inputs using different kind of ReLU functions, sorry, different kind of activation functions, and you can experiment with them like how your model is showing the output. Okay. Anyway, this is the simple theory part. Now let's do the practice it. You try to do it by yourself. If you do it by yourself, then it will be very clear to you that what's happening inside. Anyway, Let's read. In the tutorial, we saw how to build by stacking layer inside a sequential model. By adding an activation function after the hidden layers, we gave the network the ability to learn more complex relationship and non-linearity. Let me run first this one. It has imported TensorFlow. Here is the alias matplotlib for what? For plotting. These are just plotting the figures, giving figure, label size, title size. Okay. Anyway, let's do it here. Tell me what is happening here. Simple things, just reading the dataset. They have a dataset, DL course data, a CSV file. It is reading, and then the head function will show you first 5 rows. Okay, the head part of the dataset. Uh, Let me run this one. What is happening? Oh, still running. Anyway, next one is this is our task. Okay, it is done. See here. This is a concrete. That means cement. See, cement, blast furnace slag, fly ash, water. I don't know what are this. These are some ingredients in the cement. Okay, and this is the compressive strength. This is our output, and all these things are input. So you can see 1, 2, 3, 4, 5, 6, 7, 7, 8. So 8 input and 1 output. Okay. They have asked for input save. This one we did in our last class also. You can write 8 because you can see that it is 8. So if you run this, it will show you it's okay. Okay. So these are ingredients in a cement and what is the strength of the cement. Okay. If you want, you can simply just remove this and then run it. You will be able to see the solution and the hint. Okay. Anyway, next one is define a model with hidden layers. Now create a model with 3 hidden layers, each having 512 units and a ReLU function. Be sure to include an output layer of 1 unit and no activation function. Let's create the model. So first we have to write keras dot sequential. Now within the list you have to create the layers. Okay, first 3 hidden layers. Okay, so keras dot sequential layers dot dense and having 512 units. So I will write units equals to 512. Activation is ReLU. So activation equals to ReLU and anything else you have to just mention the input save. So input save equals to input save. Because here we have already set input save equals to 8, so it will take this parameter value directly. Fine. Now create the next layer. Next layer, layers dot dense and units equal to 512. Just let me give a, yeah, fine. Comma, activation equal to same ReLU. So 2 layers are created, but they have told 3 layers. So what I have to do, one more layers. So layers dot dense, you can copy also. It is better in fact. Units 512 and activation equals to ReLU. Okay, so done. Now next we have to create the output layer. So we can simply write layers dot dense units equal to 1. Okay, and in the output layer 1 unit no activation, so I will not write any activation. Okay, and input save as an argument to the first layer. We have done this. Now let's run it. See. Okay, activation. I'm so sorry. Fine. You can first, if you can't, then first click the hint, then see the solution. Okay. Now activation layers. Let's explore the activation function sum. The usual way of attaching an activation function to a dense layer is to include it as part of the definition with the activation argument. Sometimes you will want to put some other layer between the dense layer. That simply means that here what we are doing, we are creating the dense layer With that, we are also giving the activation layers. But see, there may be some scenario where you have the dense layer, you create one more dense layer, then you put the activation layer. You understand my point? In the dense layer, I don't want to put the activation on that. I want to create one more dense layer. Then maybe at the end, I want to put the activation layers. Okay, so for that, what you can do? For that, they are asking you to create separation. Separate for dense layer, separate for activation layers. Okay, see here, layers.dense, you need 8. Then you create activation layers. Layers.activation relu. So that both of them doesn't get combined. Okay, so let's change it. So, okay, so let's rewrite this. So layer.dense 32, activation relu, we have to delete this. In the first layer, there will be only inputs and the input set. Fine. In the second layer, it will be layers dot activation. Because we have created the dense layer and now we are creating the activation layer. We are not combining them. Simple. So here you have to delete all these things. Just write relu. Fine. In the next, you will have output. Okay. Now let's run it. Your model doesn't have the correct kinds of layer. You should have 5 layers with classes. Oh, you have to create 5 layers. Sorry, they have said it in the they have not mentioned. Anyway, they are creating 5 layers. So let's do what you have to do. Just copy paste. After you have put the dense layer, you put again dense layer. Okay. Next, I am creating another layer of activation function. Okay. Now dense activation, dense activation, dense. Dense activation, activation, dense activation, dense. That means done. Okay. Now let's run it. Okay. So just simple thing. We are creating separate layers. For dense layers, it's separate. For activation layers, it's separate. Okay. You can check from here. Now next, optional alternatives to ReLU. We have already discussed this. That this is a whole family of variants. ReLU. ReLU also have different kinds of variants, LU, CELU, Swiss, among all of which you can use in Keras. Sometimes one activation will perform better than another. So you could consider experimenting with activations as you develop a model. ReLU tends to do well. So it's a good one to start with. Let's look at the graph sum of this. See, choose the activation from ReLU or any other name and see how the graph looks. This is the ReLU activation functions. Let me run this one. Okay, ReLU looks like this because you are making it 0 for any negative value of input. If it is -1, -2, -3, it is negative. Whenever it's negative, ReLU function, the ReLU equation will make it a 0. Okay, so this is what ReLU looks like. If you just delete it and create LU, see, it looks different. What for CELU? So you just do it by yourself. You will be able to see the graph. See, this is different. Okay, here it is not creating 0. For negative also, the output has some negative values. Then in zeroth value, it will become 0. After that, the positivity is captured. Okay, so in our next class, we will study the next part. Okay, till then, bye. Happy learning. Hello everyone, welcome back to this channel. So we are doing Kaggle Learn, and as of now, we have done this lesson, a single neuron or deep neural networks. Okay, so we did the tutorial and the exercise part. Let me revise. First, we learned what is a linear unit, like uh, a neuron, a simple neuron we can say. W is the weight and B is the bias. X is the input. Y is the output, right? So we understood how we can give multiple inputs as well. Like here W0, W1, W2, all of them are weights. B is the bias and these are inputs and we are predicting the output. Okay. And also, we did the exercise where we created this simple single neuron, right? Next, we studied about deep neural networks. In deep neural networks, we have created layers, like not a single neuron anymore. You have dense layer, you have input layer, and also we studied about the activation function. There are different type of activation functions by which we can capture the non-linearity from the data, right? And it may be sigmoid, maybe ReLU, maybe 10H, but we also saw that mainly ReLU is used because it gives a good performance. But all other activation functions can be used also depending on your input type. Okay. And see here we have used ReLU function on single neuron. Then we have used stacked dense layer. This is a layer, input layer, two hidden layers, one output layer. Okay, so this is a stacking dense layer, and in every layer you have used a ReLU function. This is the graph of ReLU we studied, right? Okay. Next, we understood how we can create a stack dense layer. Okay, like what is the input shape, and define a model with hidden layers. These inside layers are hidden layers. This is the input layer because you are providing the input shape. This is a hidden layer. Sorry, this one is a hidden layer. This is also a hidden layer, and the last one is the output layer. Okay, so we have defined a model with hidden layers. Now, activation layer, they also asked that create some different activation layers. Don't include them in the hidden layer. So, what we did here, we created a different activation layer and a different dense layer. Okay, so all these things we have done, and also we saw how ReLU looks and how different categories of ReLU like ELU, SELU, how this activation function looks like. Now today we are going to understand stochastic gradient descent. Okay, first as usual we will read the tutorial, then we will do the exercise. Okay. Now first, let me read this thing. In the first two lessons, we learned how to build fully connected network out of stacks or dense layer. When first created, all of the network's weights are set randomly. The network doesn't know anything yet. In this lesson, we are going to see how to train a neural network. We have just created the setup, but we have not trained the model yet. Okay, we have not started the training part. That's what we are going to learn here. How to train. We have created the model. Now, how to train. Okay. As with all machine learning tasks, we begin with a set of training data. Okay. Each example in the training data consists of some inputs together with an expected output. Simple. Training the network means adjusting its weights. Right? What we learned that W0, W1, these are weights. So our job is to adjust the weight so that we get the desired output. So that in such a way that it can transform the features into the target. Okay. Now suppose they have given an example. In the 80 cereals dataset, we want a network that can take each cereal's content and produce a prediction for that cereal's calories. Suppose you take any cereals, there are some sugar, some amount of fiber, some amount of protein. So you can calculate depending on this that how much calories the cereal. Okay. So if we can successfully train a network to do that, its weights must be represented in some way that the relationship between those features and that target as expressed in the training data. Can you tell me what do you mean by features and what do you mean by target? Simple concept, just two word features mean here sugar, fiber, protein, how much of sugar, how much of fiber, how much of protein you are providing. And what is the target? Target means the output variable. What is the calories? Okay, so input is features, target is the output. Simple things. Anyway, in addition to the training data, we need two more things, a loss function and optimizer. Okay, so what we have done? We have just created the model. What is our job now? Our job is to train the model. And what do you want to achieve by training the model? Simple question. We just want to calculate the target, like calculating the calories. Okay. Now, how we can train the model? For that, we need a loss function and an optimizer. What is a loss function? Loss function mean Loss function means that you measure how good the network's prediction are. Okay, you have applied your model, you are predicting something. But the real output may be something else. So how close you are to the real output, how much you are guessing correct, that is what you have to be concerned about. So a loss function provides you that how much good you are, how close you are, or we can see that how much difference you have from the real output. So by using these loss function, you can improve your model. And optimizer means that how to change its weights. Sugar has its own weight, fiber has, protein has. So you can change its weight so that you can predict almost correct. Okay. So improving these weights or changing these weights is called an optimizer. Fine. So we need loss function, we need optimizer. Now let's dive deep. The loss function means we have seen how to design an architecture for a network, but we have not seen how to tell a network what problem to solve. The loss function measures the disparity between the target's true value and the value model predicts. We have just discussed different problems call for different loss functions. Suppose we are working with regression problem where you have to predict a numerical value. Or suppose you are working with some categorical functions where you have to predict the category. So depending on that, your loss function will differ. There is no single loss function. For every model, the loss function is different. Okay. So what the task is to predict some numerical values like 50 cells category or rating in red wine quality. So other regression task might be predicting the price of a house or fuel efficiency of a car, where you are just calculating a numerical value. That means you are working with regression problem. So depending on whether it is a regression problem or whether it is a classification problem, or depending on which kind of model you are using, your loss function will change. Okay. Now common loss function, we will discuss about a common loss function for regression problem, that is MAE. MAE means mean absolute error. For each prediction, MAE measures the disparity from the true target by an absolute difference. I have just said that your calculating value, this is the your prediction value. Sorry, model has predicted this value, and y true means this value is the real value. What has happened in reality. So if you calculate the difference, you will be understand that how much different your prediction is from the true value. This is what is known as mean absolute error. Okay, this is the straight line like y equal to wx plus b. Okay, this you have calculated. So point on this you have predicted, but these scattered points are the real points, the real target value. But you have calculated that your target value is lying on this line wx plus v. Now what happens? You have calculated this one. Your model has predicted this one, but the real value is this one. This is the difference. Same, you have calculated this one, but real is this one. So this is the difference. Here, difference is almost null. Same, but here also you have your model has predicted this one, but this is the real one. So there is a difference. There is a difference. There is a difference. There is a difference. So if you add all of these differences you found, then this is known as mean absolute error. You are just calculating the absolute error. Okay, so all you have to remember that this is a common loss function used for regression problems, and this is calculated by this way: a true value minus the predicted value. So here they have also calculated what is the value of mean absolute error. Anyway, beside MAE, other loss functions you might see for regression problems are the mean squared error. Mean squared error is also simple. You are just square this value. Anyway, different type of loss function can be calculated. Okay. During training, the model will use the loss function as a guide for finding the correct value of its weights. Lower loss is better. Obviously, we are looking so that the loss is less. If the loss is less, that means the points are very nearer or it is lying on the line. That means your model is predicting correct. That is what your target is, that predicting as correct as possible. So your job is to minimize the loss function. That's what your target is. Simple thing. Anyway, the model will use the loss function as a guide for finding the correct value. In other words, the loss function tells the network its objective. Okay. Optimizer stochastic gradient descent. We have described the problem we want the network to solve. But how to solve it? This is the job of the optimizer. Okay. So first we have created the network. Second, we have told that please minimize my loss. Now, how will the model do? We have to tell how will it do. Okay. But for that, we need optimizer. Virtually all of the optimization algorithms used in deep learning belong to a family called stochastic gradient descent. They are iterative algorithms that train a network in steps. How? One step of training goes like this: sample some training data, run it through the network to make predictions. Okay, just take some data by sampling. I hope you know what is sampling. It means that you are just selecting some from the population. You have 100 people, but you are taking 3 people. That is what is sampling. So you are taking some training data from the complete data set. Okay, and run it through the network to make predictions. That means you are just making the predictions. Now you have predicted. Now what you do? Second work is measure the loss between the prediction and true values. You have predicted, you have true values. So now you just calculate the difference, mean absolute error or mean squared error or any other kind of loss. So then once you calculate, you have the loss. Now what you have to do? Adjust the weights so that the loss becomes smaller. Okay, so either you have to increase the weight or you have to decrease the weight. You have to check for which uh, side the loss is the minimum. So you get my point. First, you have to take some training data set. You have to make the predictions. Then you have to make the then you have to calculate the loss, and then you have to adjust the weight. W1, W2, W3 we have studied before. You have to adjust the weight so that calculated loss becomes smaller. Okay, then just do this over and over until the loss is as small as you like. It will not be zero, but our job is to make it near zero. As much as possible, we will try to make it small. Okay. See, now let's read this. Each iteration sample of training data is called a mini batch. Simple thing that when you are taking some sampling from the training data and you are trying to calculate this fitted line, that is known as mini batch or we can say batch. But a complete round of the training data. I mean, if your training data has 1,000 points, let's say, then you are taking all the values, you are working on all the values, the complete round, that is known as epoch is going to be used a lot. So you understand the difference that mini batch means each iterations sample of training data, but when the complete round is taking, when you are going through the complete data set, that is known as epoch. The number of epochs you train is how many times the network will see each training example. That means if you give 10 epochs, that means the model will see the training examples, the data points 10 times. If you give 20 epoch, then it will be trained for 20 times. That means the network will see any particular data set 20 times. Okay. Now the animation shows the linear model from lesson 1 being trained with SGD. The pale red dots depicts the entire dataset. See this one, which are pale. These are entire dataset. While the solid red dots, while the solid red dots are mini batches. Every time SGD sees a new batch, it will shift the weights. So whenever it will see a new batch, it will shift the weight. Weight means the W and the B. B is the intercept, the y-intercept, and W is the weights towards their correct values on the match. Batch after batch, the line eventually converges to its best fit. You can see that first it is starting from here. See now slowly it is trying to converge. Once it minimizes its loss, see here. Now it has started like this, but it is in every batch, it is improving its weights, and finally, this is converging with the dataset. So, once you calculate this one, now you can see that your loss will be minimum, and that is what your main target is. Okay, you can see the loss gets smaller as the weights get closer to the true values. Fine. Next one is learning rate and batch size. Notice that line only makes a small shift in the direction of each batch. The size of this shift is determined by learning rate. See here, this is taking a small shift. This is what is known as learning rate. Learning rate we can change. Smaller learning rate means the network needs to see more mini batches before its weights converges to their best values. That means the rate at which it is learning, and you can also modify the learning rate by multiplying it with some smaller number or bigger number the way you want. That means how quick you are learning. In every batch, it is improving its weights. That is what is called learning rate. Simple concept. The learning rate and the size of the mini batches are the two parameters that have the largest effect on how SGD training proceeds. The iteration is often subtle, and the right choice for this parameter is not always obvious. Anyway, fortunately, for most work, it won't be necessary to do an extensive hyperparameter search to get satisfactory result. Adam is an optimizer that has adaptive learning rate that makes it suitable for most problems without any parameter tuning. See, there are different kind of optimizer. They have talked about one optimizer, that is Adam. Simply that there is not a single one. You have different kind of activation function, you have different kind of loss function, you have different kind of optimizer function. Depending on which type of data set you are working, you have to understand that which one will be better for you. Sometimes you have to work with more than one, and you have to try to predict that which one is giving you the best result. Okay, it's not that only one optimizer is there, Adam. Here they have talked about one optimizer. Anyway, after defining a model, you can add a loss function and optimizer with models compile method. Okay, so you have to write model dot compile optimizer equal to Adam, loss equal to MAE. Simple things. Notice that we are able to specify the loss and optimizer with just a string. You can also access this directly through Keras. Keras, you know that deep learning library. What's in name? The gradient is a vector that tells us in what direction the weight needs to go. More precisely, it tells us how to change the weights to make the loss change fastest. We call our progress gradient descent because it uses the gradient to descend the loss curve towards the minimum. Because we are trying to minimize the loss. So, suppose this is the loss curve. So, we are just trying to go in the that point where the loss is the minimum. That is why we are using gradient descent word. Stochastic means determined by chance. Okay, our training is stochastic because mini batches are random samples from the dataset. You are just taking some random samples and you are trying to minimize the loss. So this is kind of sampling, like you are taking a chance. And that's why it is called stochastic gradient descent. They have just explained why the name is like that. Example, red wine quality. Now we know everything we need to start training deep learning models. Very good. Now the data set consists of physiochemical measurements about 1600 Portuguese red wines. This was in our first lesson. I hope you remember. These are the components we have, and the target is the quality. So you can say that these are the features, inputs, and this is the output, that is the target. Fine. Also included is a quality rating for each wine. How we have to predict the quality from these measurements. We have put all of data preparation into this next hidden cell. It's not essential to what follows. So feel free to skip it. One thing you might note for now though is that we have rescaled each value to interval 0 to 1. Okay. Here they want to say that they have scaled the value. Some values are scaled here. How many inputs should this network have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See, 16.7, 11, and these are the number of rows, complete data set. We can discover by looking at number columns. Be sure not to include target. Target is the quality. Fine. 11 column means 11 inputs. So we have chosen a 3-layer network. We did this in our last class. 3-layer network means that there will be one input layer, two hidden layer, and one output layer. Okay. These networks would be capable of learning fairly complex relationships. Fine. See here, they have taken dense layer, 512 input, sorry, 512 neurons, 11 inputs, and the activation function they have taken ReLU. In the second layer, in the third layer, they have used same activations, and one output. Okay. These things we did in our last class. Deciding the architecture of your model, you should be part of the process. Start simple and use validation loss. You have to now calculate the loss. Three step creating the architecture. First step is done. Second step you have to calculate the loss. Fine. After define the model, we compile the optimizer and the loss function. They have used Adam optimizer and the loss function is MA. Sorry, error. Just vibrate minus y real or y real minus vibrate. Now we are ready to start the training. We have told Keras to feed the optimizer 256 rows of the training data at a time. That is the batch size. Batch size means some sampling data. So you are taking 250 rows at a single time. And after one batch, your weights will be optimized. Like it will be changed so that the loss becomes smaller. Okay. And you do that for 10 times in the complete data set. That is what is known as epochs. So in each batch you will take 256 rows and do this for 10 times all the way through the dataset. Fine. See, they have done. How to do this? History means they have just kept the total historical data in the history. So model.fit, I think if you have learned, you know that whenever you train any model, you have to call this fit function. And extend means the training data set. You have complete data set of 1000 points. Suppose 800 each for training, 200 each for testing. So in 800 data points, you have extend and widen. Extend means the input feature, widen means the output. Okay. So you have just taken the training data set. You have removed the testing data set because testing is not for training, right? So you have taken the training data set and in your data set you have some training inputs and widen means the output. Okay. Now what is the validation data? X valid, comma Y valid. What is the batch size? They have told that in every batch you take 256 rows. So batch size equal to 256 and do that 10 times all the way through the dataset. So epochs is okay. Now see here. In epoch 1, in the first epoch, you have 10 epochs. So they have done 10 epochs and in each epoch in one, they have trained the model. And after training the model, this is the loss. See, after every training, or what is your third step? So now our job is to, after every training, you have to minimize the loss. So the model gets optimized. See, 0.24, 0.13, 0.1181, 1117, 1010, then it has become 0.1005, 1011. It's almost same. That means the model has reached its position. So now your loss is minimum and you can see that your epochs has also been completed. Okay. Now you can see that Keras will keep you updated on the loss as the model trains. Often a better way to view the loss is by plotting it. That means if you plot it, you can understand how your loss is getting reduced. Okay. Now see how to plot this. So history DF, that means we have kept this in history. So we are just taking this history and you are creating a data frame because this is the training history. So you have to convert this training history into a data frame and then from the data frame you can plot the loss. See, this is the loss. It was bigger before, then it has decreased after every epoch. So after first epoch, it has decreased so much because for the first time your model has trained, so obviously it will decrease much more. Then also it has decreased. After fourth epoch also decreased. After six, after eight, and then it has become almost normal. That means you have decreased your losses. Okay, so you created your network, you applied a loss function, you applied an optimizer, and you have reached here. Okay. So notice how these levels of as epochs go by, loss curves become horizontal like that. It means the model has learned all it can and there would be no reason to continue for additional epochs. Okay, fine. Now let's do the exercise. See, in this exercise, you will train a neural network on the fuel economy dataset and then explore the effect of the learning rate and batch size. Okay, just let me run this first because this is setting up the plot. It is important. Here we have downloaded all the necessary libraries. This is the data set and the data set is about uh, fuel economy data set. Next cell to define the network we will use for this task. TensorFlow, Keras you have downloaded and layers so that you can create the model dot Keras dot sequential and you can calculate the model. So layers dot dense 128, that means you are taking 128 nodes. What is the activation function? ReLU input step means whatever the input step is provided from here. They have also already given the inputs. Now see, now our job is to, before training the network, we need to define the loss and the optimizer. So you have to use the model compile method. And they have also told you that you have to use the Adam optimizer and the MAE loss. MAE means mean absolute error. What type of losses we have studied right now? Mean absolute error and mean standard error. Though there are different types of losses. Okay. Okay. Now let's do this. Before training the network, you have to define the loss and the optimizer. So using the models compile method. So I can write model.compile method. Here I can provide optimizer. Optimizer here is Adam and what is the loss function? Loss equal to MA. You can give other losses as well. Okay, fine. Now let's run it. Fine. If you want, you just can. First, if you can't, first check the hint. See model.compile. Inside this, you have to write the optimizer and loss. Or you can check the solution also. Fine. Once you have defined the model and compiled it with loss and optimizer, you are ready for training. Now, train the network for 200 epochs with a batch size of 128. Okay. So, now you have to use model.fit. Then, sorry, inside that, what is the input data? X. What is the target value? Small y. Fine. Comma. Batch size. You have to just mention like this. Batch size equals to 128, comma. Epochs. Epochs equal 200. Okay. Now if I run it, see 200 epochs will, let's see. Let you can check here. See how loss is getting reduced. 0.348. Where it has not reduced. 345, 281, 316. So the loss, not every time it will reduce, but our job that is our main aim is that it gets reduced, but every time it will not be reduced sometimes. Anyway, finally we have got 0.0269. Okay, so simply we have just created the history. Now, if you want to see that how the loss curves look like, you just plot. For that, you have to convert it the history into the data frame pd.data frame, and then you have just plot the loss. See, the loss has reduced. Then this has reduced, increased, increased. Because see, sometimes it has increased also 0.28 to 0.272. Then again increased 0.300. So like that's why it is looking like this stock market curve. Okay. Anyway, finally it has almost reached 0.0269. Okay, so every batch size was 256 or something like that, 156, and the epoch was 200. Anyway, we have got it. And you can simply plot this by keeping the history. Okay, now evaluate training. If you train the model longer, would you expect the loss to decrease further? What do you think? Not every time, but sometimes. With the learning rate and batch size, you have some control. How long it takes to train a model? Because if you give training time for very long, then obviously your time will be taken more, your space will be taken, and you have to wait, and you may not get the desired result. So always you have to think that how many times you can train so that your model gives you the best output. Okay. It depends on many things, how noisy the learning curves, how small the loss becomes. To get a better understanding of these parameters, we look at the linear model, our simplest PP simplest neural network. Only single weight and a bias, and it's easier to say how the parameter is getting changed. Okay, see. The next cell will generate an animation like the one in the tutorial. Change the value for learning rate, for batch size, num examples, how many data points, and then run the cell. Okay, see here. If I run it, let's run with their code. Here they have provided learning rate, that means at which speed it is learning, 0.05. Batch size 32, num example 256. Here you are giving the learning rate. Because sometimes what happens, see, uh, it may happen that the loss is too huge and your learning takes a big jump. So your weights shifted in a bigger way. Then again it shifts in a bigger way. So sometimes what happens, it just goes from here to there, there to here, here to there, and it never reaches that point. So that's why what we do, we reduce the learning rate. Whatever it has learned, we are multiplying it 0.05. So what it happens here, you're reducing the learning rate so that instead of taking a big jump, it takes a small jump. And every time it is taking a small jump and it reaches to the exact point. But if you give too small learning rate, then also there will be a problem. See, we will see it here. Then also it may not reach the point. Here the learning rate is 0.05. Now learning rate batch size. Now means number of examples. Steps 50 through underscore. That is the slope of the data. And this is the bias of the data. See, this is the fitted line. Here it is how it is changing. And this is the training loss, and this is how weights are getting changed. This is weight W, the maroon one, and this one is the bias. Okay, if you want, you just give C how it is changing. First, notice this one. This is slowly moving. If I give 1.2, now if I run it, see what happens. See here, if I have changed the learning rate, so it will never converge because it is taking big jumps. Every time it is taking big jumps, and with that it is multiplied with 1.2. So it is becoming so big that it is never getting stabilized. Weights are also like that. Training loss is not captured even. Okay, but the best is if you give 0.7. There is nothing called best. Every time you have to change, but you have to also understand that you cannot increase its learning rate or decrease it so small. If you decrease it, then what will happen? This may be an interview question. If you decrease the learning rate, then it will be so slow that it will never reach the exact point. If you increase the learning rate too much, then what will happen? Then it will become unstable. See here how it is changing, 0.7. Okay, if you give 0.2, then see what happens. This is your job. Just give this and change the batch sizes, change this, and you just check how it is looking. Anyway, learning rate and batch size, what effect did changing these parameters have? After you have thought about it, run the cell below for discussion. Okay, let's discuss. You probably saw that smaller batch sizes gave noise or weight output updates and loss curve. This is because each batch is a small sample of data, and smaller samples tend to give noisier estimates. Smaller batches can have an averaging effect through which can be beneficial. They are telling you that reduce the batch size. Then see what happens. See, when we gave 0.2, it is almost, it is behaving different. Anyway, if you give small batch size, then also you can check. They are telling you to check. Smaller batches can have an averaging effect. Smaller learning rates make the update smaller. The training takes longer to converge. Larger learning rates can speed up training but don't settle into the minimum. So when it is too large, it may fail completely. That's what we have just seen. Okay. So try setting the learning value to a larger value like 0.99 and see this. We have given 1.2 and also we have checked. Okay. So for the day, we have completed the exercise. So as of now, we have learned how to create a single neuron. So what is single neuron? How to create a stacked dense layer? How to add activation layer? How to give model? Model.compile function, how to provide the optimizer for optimizing, and how to calculate the loss. Okay, these all things we have learned as of now. In our next class, we will learn the next lesson. Till then, bye. Happy learning. Hello everyone. Let's continue our learning from Kaggle. We have started into deep learning and we understood about a single neuron. Then we did a complete neural network. And after that, we have also learned how to apply any loss function and how to optimize any neural network using loss function and any optimizer. Right? All these things we have done as of now. And today our topic is overfitting and underfitting. As usual, we will first read out the tutorial, then we will do the exercise. Okay, let's read it line by line. Recall from the example in the previous lesson that Keras will keep a history that we saw some history function that is used to see that how a model is performing after every epoch, how the loss is getting reduced. You remember these things of the training and validation loss over the epochs. Exactly that it is training the model. In this lesson, we are going to learn how to interpret these learning curves. Okay, we saw the learning curves while plotting that the loss was getting reduced like that. So, we are going to interpret these things in this lesson and how we can use them to guide model development. In particular, we will examine at the learning curves for evidence of underfitting and overfitting and look at a couple of strategies for correcting it. Okay. Interpreting the learning curves. You might think about the information in the training data as two kinds, signal and noise. Signal means is that part that generalizes the part that can help our model make predictions for new data. That is the pattern, the hidden pattern. That is the signal. Like how our data is behaving with given conditions for the given features, right? And the noise is the true of the, that is only true of the training data. The noise is all of the fluctuation that comes from the data in the real world. It's like that when you train a model, you can see that data follows a pattern, but with that, there must be some fluctuations, some random fluctuations that comes from the data in the real world. Okay, or all of the incidental, non-informative patterns that can't actually help the model make prediction, which actually deviate from the predictions. From the signal, we can predict what is the hidden pattern. So, what will be our future output? But noise exactly is the kind of randomness or fluctuation that doesn't help you to make the prediction. But that is true, that is real. So, you always have to consider that also, right? The noise is the part that look useful but really is not. Now we train a model by choosing weights or parameters that we saw that whenever we are creating a model, we are using some weights W0, W1, W2. Those are the parameters we use to tune those W0, W1 and W2 so that the loss gets reduced. You remember these things? That minimize the loss on the training set exactly. You might know, however, that to accurately assess a model's performance, we need to evaluate it on a new set of data. That is the validation data. Okay, so you are keeping a different set of data. That is validation. That is not used for training. Okay, you have trained the model on training data part, but you are keeping a separate set of data like you used to keep for testing. Now you are keeping a separate set of data for validation data so that you can check how your model is performing. So you understand that your data set is divided into three parts now. Earlier it was training part, test part, but now we have created one more set of data which is the validation part. So training part, validation part, test part. All these data sets are different. That means a single data set is divided into three parts. Fine. Why validation is used? To see how the model is performing. Okay. Now when we train a model, we have been plotting the loss on the training set epoch by epoch, that we saw that after every epoch means, what is epoch? You remember that when it goes through all the points of the data set, it is known as a epoch. Okay. Anyway, after every epoch, the loss will be reduced because we are tuning weights in that way so that the loss gets reduced and our model predicts better. Now, to this, we will add a plot on the validation data too. You have created a new data set for validation data. So, you are similarly plotting on this validation data also. These are known as learning curves. Learning curves because after every epoch, it is learning something, it is reducing the loss, it is almost approaching the real output. Right? That's why these are known as learning curves. Now, to train deep learning models, we need to able to interpret them. Obviously, then only we will be able to improve our model. See, after every epoch, the loss in the training dataset is reducing this way. First, it will reduce in a speedily manner. After that, it will be kind of horizontal, right? But in case of validation, see what is happening. Loss is getting reduced, but after that, it is again getting increased. That means it is not performing right here because here the loss is reduced to the minimum, but after that loss is again increasing. Okay, so we have to make these things okay so that it gets reduced for training, it gets reduced for validation also. Okay, so the validation loss gives an estimate of the expected error on unseen data. Because this is unseen. Training data means the model has seen this data, and that's why the loss is getting improved, getting reduced. But this is not seen by the model. This is unseen. That's why after a certain time, it is again getting increased. So we have to stop this one. Okay. Anyway, let's see. Now the training loss will go down either when the model learns signal or when it learns noise. Because in your data set, you have signal, you have noise. Signal means the true pattern, noise means the fluctuation. So here, as your model can see the data set, so it is learning the signal also, it is learning the noise also. But the validation loss will go down only when the model learns the signal. Learning the signal is the correct thing, so the validation is getting lost. Sorry, getting reduced. The loss is getting reduced. Okay, but when it learns noise, a gap is created in the curve. Here it is learning the noise, so there is a problem. The size of the gap tells you how much noise the model has learned. Okay. Okay. So ideally we would create models that learn all of the signal and none of the noise. Ideally, but this is not problem. This is practically never happen. Instead, we make it trade because in your data set you must have signal, you must have noise. So you cannot do that you will learn the signal and you will never learn the noise. That will never happen. So what we you can do, you can find the balance, you can find the best of the two, you can do a trade. Now what we can do, we can get the model to learn more signal at the cost of learning more noise. So long as the trade is in our favor, the validation loss will continue to decrease. Okay, the trade is in your favor, so it will also decrease. The validation loss will continue to decrease. But after a certain point, the trade will go against you. So the cost exceeds the benefit and the validation loss begins to rise. Okay. Now see here they have given two concepts, underfitting and overfitting. Overfitting means when your model is performing extremely well in the training dataset, but it is unable to perform in the test dataset. You understand the point. While training, it is doing extremely good. It is giving you a high accuracy. But when you are applying it on the training dataset, this performance is not satisfactory because it is overfitting. And why it happens? Like you think that you have memorized all the things, and in your class exam, all those questions have come which you have memorized. So you have performed extremely well. But what happened during board exam? The patterns are bit different. So what happened? You have not understood the concept. You have just memorized the thing. So you are unable to perform in the board exam. So you understand what happened. You have memorized the things because you have seen those questions. So what happens? See this data. The model has seen this data. So the model has memorized all the data. It has not understood the exact pattern. The exact pattern is the true curve, the dotted curve. See here. This is the exact pattern. This is how data is behaving. Okay. But what happened? The model has learned every point. So it has captured every noise, every signal, and it has overfitted the model. Okay. So this is a problem. You have to reduce this problem. How that we will learn later. And the next concept is underfitting. Underfitting means you are not studying at all. So you are neither performing good in the classroom exam nor in the board exams. Here also see this is the fitted curve, true curve, and this is the fitted curve. Just a simple curve, and both of them are like different from each other. Okay, this is the underfitting. The definition is that the model is neither performing well in training set nor in the testing data set. Okay, now let's read these things. This trade-off indicates that there can be two problems that occur when training a model. Okay, two kind of problem. Not enough signal or too much noise. That means you don't have enough signal or you have too much noise. In both scenario, you will face problem. Let's see how. Underfitting the training set is when the loss is not as low as it could be because the model has not learned enough signal. The problem is that the model has not learned at all. The model has not learned enough signal. It has not captured the value. So it is unable to perform. So the loss is not getting reduced. Fine. Next one is overfitting. Why overfitting? Because when the loss is not as low as it could be because the model learned too much noise. These are the some noise data points. See, these are just noise data points. So what happened? The model has learned the noise so much that here also the loss is not getting reduced. Okay. So there are two kind of problems. Not enough signal. If your model has not learned enough signal, you may go for underfitting. If your model has learned too much noise, it has learned everything, then also you are going for overfitting. And both of them are problems. We have to solve them. Okay. How to solve them? We have to balance. So the trick to training deep learning models is finding the best balance between the two. Okay, now let's read this. A model's capacity refers to the size and complexity of the patterns it is able to learn. For neural network, this will largely be determined by how many neurons it has and how they are connected together. Okay, so what happens if you use small number of neurons? That means you are studying for less hours. Like this way. This is not exactly related, but it will help you to understand. That's why I'm giving you the example. You are learning for less time. So what happens? You are not learning at all. So your problem is underfitting. Now the problem is second problem that you are studying for long hours and you are memorizing everything. Then you will fall for overfitting. Now read here. Model's capacity refers to size and complexity of the patterns it is able to learn. For neural network, this will largely be determined by how many neurons it has and how they are connected together. If it appears that your network is underfitting the data, you should try increasing its capacity. You can increase the capacity of a network either by making it wider or by making it deeper, adding more layers. Let me draw this for you. First, let's imagine that uh, you have a neural network, sorry, for two layers and you have two inputs. First input and second input. Okay. Maybe this is x1, this is x2, and these are two neurons. And now there is output layer. So if I ask you how many layers do we have, how many dense layer do we have? One input layer and one hidden layer. And output. Output is not considered as a layer anyway. So two layers. Okay. Now suppose I want to wider. So I can increase the capacity of a network either by making it wider. That means adding more units to the existing layers. So this layer is already existing. What I am doing, I am adding the units. So I am adding 1, 2, 3, 4. Okay. And I am passing the inputs to them as well. Okay, you get my point. This is the way you are making the neural nets wider. Fine. Or making it deeper. How we can make deeper? By adding more layers. Like instead of having the output directly, what I am doing, I am creating more layers like this. And then I am keeping the output layer. Okay, so this way also you can join like this. You can join every node. So what is happening now? You have more number of layers. This is also a dense layer, and this is also a dense layer. Okay, so you can uh, increase the capacity of neural networks by adding more number of units or by adding more number of layers. So by making it wider or by making it deeper. Fine. Wider networks have an easier time learning more linear relationships, while deeper networks prefer more non-linear ones, which is just better, depends on the dataset. See, we did this before also. Keras library, sequential layers.dense, that is, you were creating a dense layer, 16, number of 16, sorry, um number of units is 16, and the activation is ReLU function. For output, a dense layer and one unit, because maybe you are doing a regression problem. Fine. Now you can make it wider. How to make it wider? By using existing layers. So, sorry, by using more units to the existing layers. So here you are increasing the unit. So you are making it 32 instead of 16, almost double. And sorry, double. And activation is ReLU. And the layer dot dense, this is for output. Okay. How can you make it deeper? By adding more hidden layers. Here first you have added 16 layers. Again you have added one more layer. First you have added 16 units to the layer. Again you have added one more layer of 16 units. Okay, so that's what I have explained you here. That's what they have done by coding. Here it is increasing the units. Here it is increasing the number of layers. Both of the way you can use for increasing the model's capacity. Now, which one you will use, that depends on the data set. Okay. For linear relationship, you may use the wider one, or for non-linear ones, then you may use that increasing the number of layers, making it more deeper. Okay. Now, next concept is early stopping. We mentioned that when a model is too eagerly learning a noise, the validation loss may start to increase during training. To prevent this, we can simply stop the training whenever it seems the validation loss is not decreasing anymore. Whenever you are training your model, you can see that it is getting reduced. But whenever you see that the validation is not getting reduced anymore, you can stop the training here, because you can also see that maybe in the training set it is performing well because it is able to see the data points, but here it is unable to see the data points. Your model cannot see these data sets, this data point. So what is happening? It is not performing well. The loss is not getting reduced. So though it may seem that it is performing well, but it is not actually performing well on the unseen data. So what we can do after we have reached the minima, after we have reached the minimum loss, minimum validation loss, we can stop training. Okay, so for that you have to see where it has stopped the it has stopped reducing the losses. There you will stop the training. Okay. So once we detect that the validation loss is starting to rise again, we can reset the weights back to where the minimum occurred. This ensures that the model won't continue to learn noise and overfit the data. Okay, here it is getting reduced. The loss is getting reduced because it is trying to memorize every point. So as it is learning each and every point in the data set, whether it is signal or it is noise, it doesn't matter. It is just a learning and the loss is getting reduced. It seems to be that our model is performing well. But the thing is that this is learning the noise, this is memorizing the things. And that's why on the unseen data, it is not performing well. Okay. Now, training with early stopping also means that we are in less danger of stopping the training too early because we are watching, then only we are stopping before the network has finished learning signal. So, besides preventing overfitting from training too long, early stopping can also prevent underfitting. Obviously, because you are not suddenly stopping here or here where model has not learned at all. So, you are removing the underfitting problems also. You are removing the overfitting problem also. You are exactly catching the point. Okay. Now just set your training epochs to some large number and early stopping will take care of the rest. Very good. Now adding early stopping. How? Now we have learned what to do to stop the overfitting and to stop the underfitting. See here it is written as underfitting. If you stop here, it is underfitting. The model will be underfitted. If you stop here, the model will be overfitted. So you have to stop exactly here. But how? How to write the code? See, for that you have to import early stopping. We include in Keras, we include early stopping in our training through a callback. A callback is just a function you want to run every so often when the network trains. These early stopping callbacks will run after every epoch. After every epoch, it will be called. Okay. Now, Keras has many predefined, but if you want, you can create your own. Here, see minimum delta, that is minimum amount of change to count as an improvement. They have set a point. Presence, after how many epochs uh, you will stop the training. And restore best words equals to true. Okay. Now these parameters say that if there has not been at least an improvement of 0.000 in the validation loss over previous 20 epochs, then stop the training and keep the best model you found. It means that if there is not 0.001 improvement, then you stop there. Don't train anymore. Okay, and now find where is the best fit model. What are those weights for that model was fitted best? Okay, it can sometimes be hard to tell if the validation loss is rising due to overfitting or just due to random batch variation. The parameter allows us to set some allowances around when to stop. As we will see in our example, we will pass the callback to the fit method along with the loss and optimizer. Okay, let's continue developing the model. We will increase the capacity of the network but also add an early fitting. Fine. Now let's increase the capacity of network. We will go for a fairly large network but rely on callback to hold the training once the validation loss shows sign of increasing. Okay. See here, early stopping equal to callbacks dot early stopping minimum delta, that is minimum amount of change that is considered as an improvement, and 20 epochs restore best words equal to true. Okay, now see here model is set. First, I have used 512 units, activation ReLU, input set, you know that number of features. Layer.dense, the hidden layer, layer.dense, again hidden layer, and this is the output layer, layer.dense 1. Now you have used Adam optimizer and loss function MAE. It will calculate the loss. Okay. After defining the callback, add it as an argument in the fit. So we have to use model.fit and extend y train. You have to pass the training data set, validation data now, x valid, y valid. I have told you that the data set is divided into three parts. That's what we are doing as of now. So now you have X valid, Y valid also. Batch size you have provided, and epochs means total number of your model will see the data points, and here callbacks equal to early stopping. What we have defined here. Okay. Now, verbose equal to 0 means turn off the training log. History underscore df, where you have kept the history, that history, you are converting it into the data frame, and now you are plotting that. So, you are plotting loss, validation loss dot plot. Now, see here, blue color is the loss, and this one is the validation loss. Okay. And sure enough, Kira stopped the training well before the full 500 epochs. Okay, this is the maximum epoch. Mm, Before that, you have to stop it. Fine. Now predict your turn. Okay, let's do the exercise. Okay, so what we have learned here? We have learned how to use the early stopping so that we can prevent overfitting and underfitting. Now, in this exercise, you will learn how to improve training outcomes by including an early stopping callback to prevent overfitting. Exactly when you are ready, on the next cell, we are ready, we have run. First, load the Spotify dataset. Your task will be to predict the popularity of a song based on various audio features like tempo, danceability, and more. Import matplotlib plot.style.use for matplotlib set label size, title weight, title size. Learn tools.core, import binder, and all these things. Later on, we have imported pandas, standard scaling, one hot encoding, column transfer, spotify.csv, and then they have done some EDA part, see features, num features cat, then they have done the column transformation, group split. See here it has xtrain, x valid, y train, valid, and group split xy artist. Okay, now you have training data set, you have validation data set. Okay, fit transform for xtrain, and for transform for and transform for x valid. Okay, and y train also you have, y valid also you do have. Okay, let's start with a simplest network. This model has low capacity because you are using small number of units. Now let me run this one. See, model equal to keras dot sequential layers dot dense one, only one layer. Model dot compile optimizer Adam, loss equal to MAE, and history equal to model dot fit. You send extend, y train, you send validation data, batch size, epochs, and verbose. Now you convert the history to a data frame, you plot it. Okay, now see what happens. Loss, validation loss. So minimum validation loss is 0.1951. It's not uncommon for the curves to follow a hockey stick pattern. This makes the final part of the training hard to see. So let's start at epoch 10 instead, because you cannot see what is happening here. Okay, so we will start with epoch 10. Now let me run this. See what happens. Now you can visualize. This is the loss. This is the validation loss. Okay. Now evaluate the baseline. What do you think? This is underfitting or overfitting? Think. Okay. Before you see, you just pause it and think. This is the loss. This is the validation loss. Validation loss is lower than the loss. So it is overfitting or underfitting? Obviously it is underfitting. Okay. So let me run this. The gap between these curves is quite small. Validation loss never increases, so it's like underfitting. Once it starts increasing, then only we'll consider it overfitting, right now? Let's just see here. Here it is underfitting because it is not getting increased. When it will start increasing, then only we can see that this is overfitting. And why it is underfitting? Because we have not used any neurons, any units. So you have to add some units. Uh, add some capacity. So we will add three hidden layers. First 128 unit, then 64, and 1. Run the next cell to train the network and see the learning curves. Let me first run it. Compile optimizer Adam loss MAE model.fit extend y train validation data batch size given epochs given. You have converted it into data frame. You have plotted also. Okay, first check the history. See here loss 0.25, 0.24, 0.19 getting reduced. Validation lost 0.20, 0.19, 0.19 getting reduced. Very good. For how long? After that, see, after 0.2005, 0.2004, it has started increasing. 13, 13. Okay. So you can see that after this, training loss is getting reduced because it is memorizing the things, because it is overfitting the data, but validation loss is not decreasing anymore. Okay. So what is your evaluation of these curves? Underfitting or overfitting or just right? Now the validation loss begins to rise very early while the training loss continues to decrease. This indicates that the network has begun to overfit. At this point, we would need to try something to prevent it, either by reducing the number of units or through a method like early stopping. Okay, so what we will do? We will use early stopping. So now this is your job. You have to write the early stopping function. Okay, so now define an early stopping callback. The wait epochs 5 patients for change in validation loss of at least 0.001 and keeps the weights with the best loss. Anyway, let's write this. Call to, we have to use the callbacks dot early stopping and here write mean underscore delta equals to 0.001 comma what are the other things, patience, so patience equals to 5 epochs comma restore best weights. Let me copy this. Restore best weights equals to um, true. Okay, within 5 epochs. Okay, now let me run this. This is fine. You can see the solution from here also. Anyway, now run this cell to train the model and get the learning curves. Notice the callbacks argument in the model fit. 128 unit, second layer 64, activation ReLU, output 1, compile optimizer Adam, loss MAE, extend wide range, validation, batch size, epochs. Now you are calling the early stopping. Early stopping which you have defined here. Okay. Now you are plotting this also. See, it will go for 50 epochs, but within that you can see that after a certain time, what is happening? It has stopped. Epoch 12 out of 50 because here after this it has stopped decreasing. Okay, it has not run for 50. Whenever it has found that the validation loss is not increasing, sorry, is not decreasing anymore, within this epochs, it has called the early stopping and this one is executed. Okay, this is actually called after every epoch. So whenever it finds that the criteria is matching, it will stop and it will restore the best weights. That is the best model. Okay. Now was this an improvement compared to the training without early stopping? What do you think? The early stopping callback did stop the training once the network began overfitting. Moreover, by including restore best weights, we still get to keep the model where the validation loss was the lowest. Okay, so our job is to find where the validation loss is the minimum. This is this point we want to find. So that is done by the early stopping. It will check after every epoch and whenever it can see that the validation is not decreasing anymore, it will stop the model and it will bring back those points where the validation loss was the lowest. Clear? I hope this is completely clear to you. And we have done it. If you like, you try experimenting with patients and mean delta. Okay. Just change the patients and change the minimum delta. Okay. And you can check out. Okay. I hope these things are clear to you and you have enjoyed the session. Let's meet in our next session. Till then, bye. Happy learning. Hello everyone, welcome back to this channel. Let's continue this course. As of now, we have completed a single neuron. We have understood how to create a deep neural network. Then we understood what is stochastic gradient descent, the loss function, the optimizer, and then how to prevent overfitting or underfitting. Okay, by using early stopping. Now today our lesson is about dropout and batch normalization. First we will read, then we will do the exercise. Okay. Let's read. There's more to the world of deep learning than just dense layers. There are dozens of kind of layer you might add to a model. We have learned how to implement dense layers in a neural network, but they are saying that other than dense layer, there are other types of layers exist. Okay. Some are like dense layers and define connection between neurons, and others can do pre-processing or transformer of other sorts. Okay. In this lesson, we will learn about two kinds of spatial layer, not containing any neurons themselves, but that add some functionality that can sometimes benefit a model in various ways. Both are commonly used in modern architecture. One is dropout. The first of this is the dropout layer, which can help correct overfitting. Overfitting, you remember, we studied in our last class. Overfitting means that the model is performing extremely well during training, but not on unseen data, not on testing data. Okay, why is that so? Because it is memorizing all the data points, like all the signals and all the random noises also. So it is memorizing every point. It has seen all the data. That's why it is performing good. It has cheated simply. You not cheated, but memorized the thing. But when performing on the testing data, it has not seen the data. It has not captured the real meaning of the data, the real pattern of the data. So it is unable to perform. That is overfitting. Now here to prevent overfitting, we used early stopping. You remember. But another way is to use dropout layer. Okay. So in the last lesson, we talked about how overfitting is caused by the network learning spurious patterns in the training data. To recognize these patterns, a network will often rely on a very specific combination of weight, a kind of conspiracy. Okay. As every units are used every time, so what happens? They may make some conspiracy of weights. So being so specific, they tend to be fragile. Remove one and conspiracy falls apart. So if you remove this one, then this unit has to be dependent on other three. If you remove this one, then it has to be dependent on all these three. So what happens? The conspiracy breaks. Okay, this technique is known as dropout technique because here you are just removing one unit. When? Which one? Then the answer is that randomly. Let's read this. To break up this conspiracy, we randomly drop out some fraction of layers input. Maybe at first epoch, I am randomly removing this two. Next epoch, I am randomly removing this two. Okay. So randomly, I am selecting some layers and I am dropping out. Dropping out means I am not using them. So the output from when it is removed, the output from this layer is not going to the next layer. Okay. So you understand that we are just making it stop. That I don't want any output from this layer. And we are selecting randomly. Why? So that the conspiracy falls apart. So that it doesn't think that this is the only way. So that it learns from this also, from different combinations, and it captures the real pattern rather than memorizing the thing. Okay, making it much harder for the network to learn those patterns in the training data. Instead, it has to search for broad patterns whose weight patterns tend to be more robust. Exactly. Now you have to find the general pattern. You can just memorize the thing. You have to understand the general pattern because sometimes it is stopped, sometimes it may be stopped randomly. Some neurons are stopped. Okay. If you have another layer also, after this also, if you have one more hidden layer, then you can use dropout layer for these layers also. Okay. Anyway, you could also think about dropout as creating a kind of ensemble of networks. The predictions will no longer be made by one big network but instead by a committee of smaller networks. So, what is happening? I am not using the big network always. I am taking some smaller networks each and every time. Different networks every time. Okay. So it will get different kind of output, different kind of pattern. So it will be able to get the generalized pattern. That means you are not taking the feedback from one person or the exact three persons always. What you are doing, you are randomly taking two persons or three persons or one persons, and you are taking the feedback so that you understand what is the general pattern. That is the simple logic. Individuals in the committee tend to make different kinds of mistakes, but we write at the same time, making the committee as a whole better than any individual. Okay. At the same time, you are not using everyone, but you are using more than one. You are not taking from any individual. You are taking from committee of smaller networks. Okay. Now adding dropout. In Keras, the dropout rate argument rate defines what percentage of the input units to start up. Put the dropout layer just before the layer you want the dropout applied to. So keras.sequential layers.dropout layers.dense. That means when you are using this layers.dropout rate equal to 0.3, it means that for the next layer apply 30% dropout. If you have 10 units in the next layer, then 3 units will be stopped every time. Random 3 units, no fixed. Maybe in the first epoch, first 3 units, maybe in the second epoch, other 3 units, like randomly. Same unit may also be selected, same unit may not be selected as well. It's like sampling. So randomly you are dropping out person in the next layer. Okay, so this is the way you can use the dropout. You have to just use the dropout function. Fine. Okay, so you have understood what is dropout, just dropping out some layer. Now our next concept is about batch normalization. The next special layer is batch normalization, or we can say batch norm. That is for when your training is slow or maybe unstable. For that you use batch normalization. What happens? Suppose in your data set you have different kind of columns. One is about height. So height may be 4 feet, maybe 3 feet, maybe 5 feet. One is about distance. That may be 150 miles, 200 miles. One more column is suppose about price, which may be 20 lakhs, 30 lakhs. So you understand that there are differences in numbers. One is 4, one is 2 lakh, one is 150. They are not in the same scale. So that may create a problem for your machine learning algorithm. Some features may get much priority over other features. They may dominate, but in reality, that may not be true. So, what we have to do, we have to bring them into a single common scale. Like maybe within 0 to 1, the minimum will be 0, the maximum will be 1, or any other minimum or maximum value. Any kind of scaling that depends on uh, how is your data set. You have to scale your data. Simple. So with neural network, it's good idea to put all your data on a common scale so that every feature gets the same priority. No feature can dominate other features. Features wins input. Perhaps with something like scikit-learn's standard scalar, min-max scalar. These are the libraries which are used for scaling the dataset. Okay. The reason is that SGD, stochastic gradient descent, will shift the network weights in proportion to how large an activation the data produces. Features that tend to produce activations of very different sizes can make for unstable training behavior. Exactly, if different features have different kinds of data and they produce activations of different sizes, then it may be unstable for the training. So you have to scale it. Now, if it's good to normalize the data before it goes into the network, as you are using many layers, and if the output from this one, from any neuron, if they are not in the same scale, they may create a problem for the next layer. For this layer, they may be a problem. Okay, so maybe also normalizing inside the network would be better. So before giving the input, we are using this standard scaling or min-max scaling. But inside the layer also we can scale the data so that the output from this layer gets normalized, and then it goes as the input for the next layer. Because output from this layer is also input of this layer. Here we are doing the standard scaling normalization. Fine. But what if here if the output is not scaled? This is also input for this layer, right? So we also have to scale it here. That is what is batch normalization. We have a special kind of layer that can do this. That is batch normalization layer. A batch normalization layer looks at each batch as it comes in, first normalizing the batch with its own mean and standard deviation. That is a technique by using you can do the batch normalization, and then also putting the data on a new scale. Exactly, with two trainable scaling parameters. Batch norm, in effect, performs a kind of coordinated rescaling of its inputs. Fine. Most often, batch norm is added as an aid to the optimization process, though it can sometimes also help prediction performance. Models with batch norm tend to need fewer epochs to complete training. Moreover, batch norm can also fix various problems that can cause the training to get stuck. Consider adding batch normalization to your models, especially if you are having trouble during training. Adding batch normalization. It seems that batch normalization can be used at almost any point in a network. Like see, here I have used layers.dense, a dense layer, 16 units, ReLU activation function. Next, you apply batch normalization layer. Okay, so what happens? Whatever the output from this layer will be normalized, will be bring into a same scale, maybe using the mean and standard deviation. See, layers.den 16, you are doing the normalization. Okay, so this is a way by which you can do batch normalization, or you can use this also. Here you are just breaking this. Like first you are creating the dense layer, then you are applying the batch normalization, then you are passing it through the ReLU activation. And if you add it as the first layer of your network, it can act as a kind of adaptive preprocessor, like standard scaler. Okay, now example. Using dropout and batch normalization, they have developed a red wine model. Now we will increase the capacity even more, but add dropout to control overfitting and batch normalization to speed up optimization. Just go through the code. Okay, matplotlib downloaded, plot.style.use, and pandas. This is the data set, train, validation data, split the data, y train, y valid, everything is set. Now you use the dropout layer. So you may need to increase the number of units in the dense layer. First one we learn dropout layer. So keras, import layers. First the dense 1024 units. ReLU activation. Input step equal to 11. Next layers dot dropout 0.3. That means 30% of the neurons will be dropped out. Fine. After that you apply batch normalization. It will be normalized by mean and standard deviation. Next, again another layer. So the normalized input output is going as an input for this layer. Again, you are dropping out some portions. You are using batch normalization. Next layer, you are using dropout. You are using batch normalization. Okay. There's nothing to change this time in how we set up the training. Obviously, you used before Adam and Amy, they have used that only. In the history, you are keeping model.fit, you are passing extend, ytrain, validation data, you are giving 256 batch size, randomly 256 data points will be taken, epochs 100 times, or was 0, you are converting it into the data frame, and you have plotted the loss. See, this is the loss and this is the validation loss. So you'll typically get better performance if you standardize your data before using it for training. That we are able to use the raw data at all, however, shows how effective batch normalization can be on more difficult data sets. See how it has performed so well at the end, right? This is due to the batch normalization. Now your turn, let's do it. In this exercise, you will add dropout to the Spotify model and see how normalization can let you successfully train model on difficult dataset. Okay, let's understand. Same, just they have created the plots and they have used that Spotify dataset we used earlier also. Let me run all these datasets. Then we have to add a dropout to the model. Okay, we will add a dropout, we will add a batch normalization. It's taking time. It's done. Okay, now let's run this. Here is the last model from exercise 4. Add two dropout layers, one after dense layer with 128 units and one after the dense layer with 64 units. And dropout 0.3, 30% dropout. Okay. So one after 128 units, one after 64 units. So simply you have to write layers dot dense, sorry, dropout, and inside that you have to mention 0.3, right? Same, you have to use 1 after 64. I've just copy pasted. Okay, now let's run this. I'm so sorry. Comma, comma. Now let's run this. Okay, just run it once. If you want, you can first take the hint. You don't need go. Dense dropout, dense dropout, dense. Exactly. Okay. Now run this next cell to train the model. See the effect of adding dropout. Same Adam optimizer, MAE loss function, history is taken, history is plotted. Same things. See, loss and validation loss. Performing well. If the validation loss is getting increased, then you can say it is overfitting. In this scenario, here it is underfitting. But you can see that here it's performing extremely well because loss and valid loss, both of them are getting reduced. Now, recall from the model tended to overfit the data around epoch 5. Did adding dropout seem to help prevent overfitting? Yes, obviously. From the learning curves, you can see that the validation loss remains near a constant max minimum, even though the training loss continues to decrease. So we can see that adding dropout did prevent overfitting this time. Okay. Earlier it was not like that, it was overfitting. So moreover, by making it harder for the network to fit spurious patterns, dropout may have encouraged the network to seek out more of the true patterns. Exactly. So don't just learn the spurious patterns. Instead, use different kind of committee of smaller networks and try to find the true patterns. Okay, now we will switch topics to explore how batch normalization can fix problems in training. Load the concrete dataset. We won't do any standardization this time. This will make the batch normalization much more apparent. Just we have downloaded the dataset. We have not performed any standardization this time so that we can understand how batch normalization is um, having an impact. Just here we have downloaded the dataset and they have made a copy and it is dropped. Extern is set. Y train. Output is the compressive strength. So Y valid, X valid, Y valid. Input shape is also taken. Let's run. Okay, done. Next is run the following cell to train the network on unstandardized concrete data. Keras.sequential, dense layer, dense layer, dense layer, model.compile. Optimizer SGD is used here because this is more sensitive to differences of scale. Adam is not taken. Loss MAE. Matrices also MAE. History is plotted. So pd.data frame history.history. Same. It is let it run. See, you can find a blank graph. Did you end up with a blank graph? Trying to train this network on this data set will usually fail even when it does converge due to lucky weight initialization. That means if it even converges, it tends to converge to a very large number. So what is happening? Actually, it is getting failed, but even if it converges due to some good initialization, that lucky initialization, that may converge to a very large number. So that's why we are actually getting failed. Now we are going to use our techniques, which is batch normalization. Okay, now this problem can be solved by adding batch normalization layers. Batch normalization can help solve this problem. Okay, they have told you add 4 batch normalization layer, one before each of the dense layer. So you have to write layers dot batch normalization, and you have to pass the input. Okay, now remember to move the input step argument to the new first layer. Okay, done it. So this one will be deleted. Next, again, you have to put the batch normalization layer, give a comma, and after that, put it here and after every dense layer. So maybe there also. Okay, but sorry, you have to put the comma. This is a class, right? Now let's run it. See, correct. Okay, run the next cell to see if it will let us train the model. Just okay. Now let's do this one. Evaluate batch normalization, optimizer SGD, loss MAE, matrices MAE, epochs 100, history. Let's plot it. See how it is performing after adding the batch normalization. Okay. See. Okay. Earlier it was completely blank because it was converging to a large number, or it may have failed, but this time it is working nice. Validation loss and the loss are close to nearby. So batch normalization is giving you. You can see that at batch normalization was a big improvement. By adaptively scaling the data as it passes through the network, batch normalization can let you train models on difficult data sets. Okay, so we have completed the task. So let's meet in our next class. Till then, bye. Happy learning. Hello everyone, welcome back to this channel. Let's continue our Kaggle Learn Intro to Deep Learning. And we understood what is a single neuron, how to create a dense layer, how to create stacked layer, the deep neural network, and then we understood what is stochastic gradient descent, how to use the loss function, how to use the optimizer, then we understood what is overfitting, what is underfitting, and how to prevent overfitting by early stopping. We also understood what is dropout layer, like removing the some of the units from the layer, and we also understood why batch normalization is required and how to do the batch normalization. Okay, now we are going to understand the last lesson of this course, that is binary classification. We will first read, then we will do the exercise as we do. Okay, now let's read. So far in this course, we have learned about how neural networks can solve regression problems. Okay, we have understood this as of now. Now we are going to apply another common machine learning problem, that is classification. Whenever you work with any machine learning problem, you have to face either regression problem or classification problems mainly. Okay, so you understood how to solve the regression problem as of now. Now our focus will be solving the classification problem. What is classification problem? When you classify whether it's a dog or it's a cat, whether yes or no. These things are known as classification problems. Okay. Most everything we have learned up until now still applies. Whatever we have learned till now for regression problem applies for classification problems also, with some moderate changes. That is what we are going to learn today. Okay. The main difference is in the loss function we use. and in what kind of outputs we want the final layer to produce. Okay, so the difference is that the loss function. Do you remember which loss functions we used while doing the regression problem? We used minimum absolute error, or you can use minimum squared error. There are many loss functions. So the difference is that when you use regression problem, you have to use a different loss function. For classification problem, loss function will be different. And what kind of output you want? In regression problem, you will have only one output, but in classification problem, you may have more than one output. Okay. So this is the simple difference between regression and classification problem. All other things are almost similar. Now, binary classification. Classification into one of two classes is a common machine learning problem. You might want to predict whether or not a customer is likely to make a purchase. You want to know whether a customer want to make the purchase, yes or no. Whether the credit card transaction was fraudulent, yes or no. Whether deep space signals show evidence of new planet or a medical test evidence of a disease. These are all binary classification problem. Binary 0 1 like yes or no. Two outputs. Two outcome. Okay. Now, in your raw data, the classes might be represented by strings like yes or no, dog or cat. Before using this data, we will assign a class level. One class will be 0, other will be 1. Okay, that is what classification problem. Okay, now assigning numeric levels puts the data in a form a neural network can use. When you give them a numerical value like 0 or 1, then a neural network and use that. Okay. Now accuracy and cross entropy. Accuracy is one of many matrices that is used for measuring success on a classification problem. Like how much successful you are. So you want to know how much accurate you are. Like within 10 mathematical questions, you have performed 8 correct. So you can understand that your accuracy is 80%, 8 out of 10. Okay. That measures how good you are, how successful you are. Okay. So accuracy is the ratio of correct predictions to total predictions. Accuracy equal to number correct divided by total. How many correct? 8 questions are correct divided by total 10 questions. So your accuracy is 8 out of 10. A model that always predicted correctly would have an accuracy score of 1.0. Yes, because every time it is correct. So number of correct is equal to total. Whenever both are equal, it will be 1.0, it will be 1. All else being equal, accuracy is a reasonable metric to use whenever the classes in a data set occur with about same frequency. Okay, now the problem with accuracy is that it can't be used as a loss function. SGD needs a loss function that changes smoothly. Like whenever you are changing your weights or biases, there will be differences in losses. So you need a smooth change. But what accuracy does, it changes so abrupt. So it being a ratio of counts changes in jumps. That's why accuracy is problematic for some scenario. So we have to choose a substitute to act as the loss function. And the substitute is cross entropy function. Instead of accuracy, we will use cross entropy because it changes smoothly, not like accuracy, not that abrupt change. Okay. Now recall that the loss function defines the objective of the network during training. With regression, our goal was to minimize the distance between the expected outcome and predicted outcome. That's how we calculated the loss. There was some expected outcome, there was some real output, that is the expected output, and there was some predicted output. And whenever we calculated the distance, we found the loss. Okay, during regression, you remember these things, I hope. Okay, anyway, so we chose MAE to measure this distance. You can choose anything like mean absolute error, mean squared error, like anyway you can choose, but we used this one. If you remember, we used optimizer Adam and loss MAE. Okay, but for classification, we want is a distance between probabilities, and this is what cross entropy provides. Cross entropy is a sort of measure for the distance from one probability distribution to another. Let's say you have an image of a cat. Now you want your machine to predict whether the image belongs to a cat or the image belongs to a dog. Okay. Now first what you have to do, you have to calculate the probability. So I calculate that it is 80% probable that the picture is of a cat, and 20% probability is that the picture is of a dog. Okay, so there is a distance between the probabilities. That is what cross entropy provides. Okay, so it is a sort of measure that distance from one probability distribution to another. Now, when will your model perform the best? When your probability of being a cat is 100% and the probability of being the image of a dog is 0%. Okay, so cross entropy measures the distance from one probability distribution to another. So whenever you are making wrong predictions, like you are making your probability is like 60%, 50%, 40%, that means your cross entropy will be high. But when you are doing good predictions like 80%, 85%, 90%, that means you are going towards the accuracy. So then your cross entropy will be low. Okay, so our job is to make the cross entropy low. Then only our model will perform better and will predict the best. See here how the loss is getting reduced. Like you have predicted that the image belongs to a dog. So loss was high. But when you have predicted that 20% belongs to a cat. So you are predicting some amount, so your get loss is getting reduced. You are predicting 40%, your loss is again getting reduced. You are predicting more, that 60%, then it is getting reduced. You are predicting 80%, you are predicting the correct class probability 80%, so you are doing much better. And when you predict that it is 1%, sorry, 100%, that means you are predicting exactly right. Okay, so our job of cross entropy is to measure the distance from one probability distribution to another. It will be high when we have bad predictions of probability, but it will be low when you are making good assumptions of the probability, good predictions of probability. Okay, now see, the idea is that we want our network to predict the correct class with probability 1.0. That is the ideal scenario. The farther away you are from the predicted probability from 1.0, the greater will be the cross entropy loss. The farther you are, the loss will be more. Okay, that's what we have discussed. The technical reasons we use cross entropy are a bit subtle. But the main thing to take away from this section is just this. Use cross entropy for a classification loss. Other matrices you might care about will tend to improve along with it. They are saying that use the cross entropy for the for this classification loss. Just calculate this one. What is your cross entropy? Then only you will be able to understand how much far you are from the real value. Okay, and other matrices will automatically improve. That's what they have said. Now, making probabilities with the sigmoid function. The cross entropy and accuracy functions both require probabilities as inputs. So, as input, you have to provide the probabilities for cross entropy and accuracy functions. That means numbers from 0 to 1. Now, to convert the real valued outputs produced by a dense layer into probabilities, whatever the output is from the dense layer, you have to convert them into probabilities. For that, we use a new kind of activation function, that is sigmoid activation. Okay, this is the sigmoid activation function. There do you use the ReLU function. The graph of ReLU function was like that only. It was making negative to 0. Anyway, for classification problem, we will use the sigmoid activation function. Okay, see, this is the graph. Uh, this is for positive points and this is for negative points. Okay, this is the sigmoid activation function. Now to get the final class prediction, we define a threshold probability. Typically, this will be 0.5 so that rounding will give us the correct class. Below 0.5 means the class with level 0 and 0.5 or above means the class with level 1. Okay, it's just like that you are giving an exam and if you score more than 60%, that means you are getting passed. If you score less than 60%, you are getting failed. So there is a threshold that is 60%. Here also, if the probability of the image being a cat is 60%, more than 50%, then I consider it as to be image of cat or I consider it to be an image of something else. Okay, so here you are setting a threshold probability. You can set any number, but typically it is set to 50%. If you want, you can give also 80%, that if the probability of the image being a cat is more than 80%, then only I will consider it as an image of cat, else I will not. So any threshold you can set, but typically we set 0.5. Whenever you are getting something, some probability more than 50%, that means you are you may class it as level 1, or you may class it as level 0. Okay, this is in Keras used by default. Now example, binary classification. Now let's try it out. Okay, the ionosphere dataset, they have provided a dataset that has features obtained from radar signal focused on the ionosphere layer of our atmosphere. Now the task is to determine whether the signal shows the presence of some object or just empty air. Anyway, let's see, this is the dataset. You have downloaded the dataset. Then uh, just created this is the dataset, and this is the class, good bad. So you can see this is the classification, so you have to predict whether it's good or whether it's bad. Now we will define our model just like we did for regression task, with one exception. In the final layer include a sigmoid activation so that the model will produce class probabilities. Okay, it will just be like what we did before, but we are going to use sigmoid activation function, because sigmoid activation function will decide whether it belongs to dog or it belongs to cat. Okay, now see. So from TensorFlow, import keras as usual, import layers as usual. You have created a dense layer. Okay, no problem. 33 inputs because they have 33 columns. Fine. Now add the cross entropy loss and accuracy metric to the model with its compile method. Exactly. You have to give the optimizer Adam they have provided, or for two class problems, be sure to use binary versions. Exactly. Here, good or bad, only two types. So they are using binary. Okay, it may be more than one class also. Here only they have considered binary versions. Okay, Adam optimizer works great for classification too. So let's stick with that. And what is the loss function here? Binary cross entropy. For regression, what was the loss function? MAE. Okay, here we are using. It's not fixed. Anything you can use, but typically it is used. Okay. Matrices is binary accuracy. The model in this particular problem can take quite a few epochs to complete training, and for that we are going to use callback function. You remember callback function, early stopping callback function um, for correcting the overfitting, right? Now early stopping equal to keras dot callbacks dot early stopping patience 10 minimum delta value and restore best weights. Whenever it finds that the validation loss is getting increased, it stops the training and it restores the best weights for which the validation loss was minimum. I hope you remember these things. If you have not, you see the previous video. Okay. Now history equal to model.feed extend y10 validation batch size epoch callback early stopping, and verb was equal to 0. It is kept in history, then it is converted to data frame as usual, and we have plotted this. Okay, now see. This is the best validation loss, 0.3534. Validation loss, this is the loss. Whenever you increase the gap, what does it mean? That means your model is overfitting. This is the binary accuracy plot. Okay. Now use a neural network and predict cancellation in hotel reservations. Okay, fine. Let's do the exercise now. So in this exercise, you will build a model to predict hotel cancellation with a binary classifier. First, you have imported matplotlib, plot.style.use, plot.rc, matplotlib defaults, set up feedback system, and first load the hotel cancellation dataset. Okay. After this is done, we will load the hotel cancellation dataset. We have to predict whether any customer will cancel the hotel or not. So it is a classification problem, yes or no. So that's why we have to change the activation function. Okay, all other things you can see that almost same. It is done. From scale and model selection, import trend test split, standard killer, one or EDA part, simple imputation, arrival date month. These are the features, numerical features. These are the categorical features. You have to convert the categorical features into numerical features. Then you have created extend y trend. Okay, this part is fine. Now define model. The model we will use this time will have both batch normalization. Batch normalization, you remember, for normalizing the inputs, for bringing them into a single scale, and dropout layer. Dropout layer means so that the it can stop memorizing. Instead, it understand the pattern. That's why what you do, you make some outputs from some neurons to 0. Okay, and every time you select the dropouts randomly. Now to ease reading, we have broken the diagram into blocks, but you can define it layer by layer as usual. So define a model with an architecture. This is the diagram you have to follow. See here. First, batch normalization, input step equal to input step. Then all these steps we have to follow. Okay, no problem. So just delete it. These are imported. So first I have to write batch normalization. So heras dot sequential, and then I have to first give batch normalization. So sorry, layers dot batch normalization, and input step equal to input step. That means how many features you have in your data set. Okay, fine. Uh, Next layer, dense 256 activation value. So layers dot dense layer units equal to 256, activation equals to ReLU. Fine. Next, layers dot batch normalization. Next, dropout 30%. So layers dot dropout. That means randomly you will delete outputs from some neurons. 30%. That means within, if you have 10 units, then you will drop 3 units randomly. Again the same setup. See, batch normalization 0.3. So we can just copy this. Layers dot dense activation ReLU, batch normalization dropout. Fine. And the last one is sigmoid activation. Okay, so layers dot dense. Here sigmoid activation is required so that you can create a threshold between probabilities and calculate the final output. Okay, if it is more than 50%, the output will be different. If it is less than 50%, the output will be different. For that, you need a sigmoid function, okay, which will calculate the output. Now, let me run this. Mm, Here also. Okay, now let's see. Okay, fine. Okay, now add optimizer, loss and metric. Now compile the model with Adam optimizer. So we can write model dot compile. Here optimizer equals to Adam comma binary versions of cross entropy. So loss equal to not MAE but binary cross entropy. Okay, and matrix equal to binary underscore accuracy. Okay, I think it's done now. Let's run it. Okay, just run this once if you want to. Sorry. You want to check the solution. Okay, loss matrix. Now finally run this cell to train the model and view the learning curves. It may take for 60 to 70, which could take a minute or two. Okay. So here what is happening? We are creating the early stopping function. Okay. Patience, minimum delta and restore best weights. Now you are training the model. So model.fit, extend y10, validation data, batch size, 200 epochs. We may have make it lesser. And callbacks equal to early stopping. Okay. So whenever it finds that the validation loss is getting increased instead of getting reduced, it stops it and it restore the best weights. Okay. And all these things are kept in a history which is converted into a data frame and which can be plotted after the model is trained. So now we are in 16th epoch. So it will take time. You can check the losses like 0.4855, 0.4244, 414039, getting reduced 38, getting reduced. What about validation loss? That is also getting reduced. So it will go on. See, uh, now it is not getting reduced anymore. 13566, 13544, 13532. If again there is a great gap between loss and validation loss, then the training will be stopped. But the loss is 0.34, validation loss is 0.35. They are still near to each other. Okay, whenever the loss will get reduced, whenever the loss will reduce, but the validation loss will not reduce, then only the early stopping will work and the training will be stopped. For now, it will run. Okay, see, it's done because after that it has started increasing. After this point, it has started increasing. So, training has been stopped. Okay, it only in 42 epochs within 200 epochs. Fine. What is about accuracy? Binary accuracy and validation, binary accuracy on the validation data. Okay. So now what do you think about the learning curves? Does it look like model underfit or overfit? Was the cross entropy loss a good stand in for accuracy? Okay. What do you think? Model is underfitting or overfitting? No, it's not. Was the cross entropy loss a good stand in for accuracy? Yes. Let's check. Though we can see the training loss continuing to fall, but the early stopping callback prevented an overfitting. Moreover, the accuracy rose at the same rate as the cross entropy fell. So it appeared that minimizing cross entropy was a good stand-in. And all in all, it looks like this training was a success. Because see, the accuracy is getting improved and the loss is getting reduced. Okay. So if the loss was also reducing more, but the validation loss was not increasing anymore, so that's why we have stopped it. We have called the early stopping, and now you can calculate the binary accuracy and the model is performing nice. Okay, so congratulations, you have completed Kaggle's introduction to deep learning course. With your new skills you can do these things. Do you want me to make videos for on these things also? If you want, you can let me know in comment section. Anyway, so what are the things we have learned as of now in our complete course? We have learned how to create a deep neural network, how to calculate the loss function, how to calculate the optimizer, how to check whether it is underfitting or it is overfitting, what is validation loss, then how we can stop the overfitting, how to use dropout layer so that the model does not overfit, and how to use the batch normalization. So next, we understood how to do the binary classification problem, how to do the regression problem, and how to work out with the binary classification problem. And also, we understood how to use the sigmoid function. Where to use the sigmoid function? In the last output, where you are predicting whether it will be the image of something else or of something else by giving a threshold value. Okay, so I hope you have learned the things. I meet in our next video. Till then, bye. Happy learning.